But for the sake of using the hour as much as we can, I'm just gonna get started. Welcome to the AstroAI lunch talk. Today I am extremely delighted to have Liam Connor. Liam joined the Harvard astronomy faculty recently. He's an expert on radio astronomy and fast radio bursts, how to find them, how to characterize them, what sort of environments they live on. And for that, he works on building radio telescopes, building tools of AI. That is what he's going to be telling us about today, in order to investigate these objects and other objects in radio astronomy. So Liam got his PhD from the University of Toronto, and after that, he spent some time at Astron in Amsterdam, the Netherlands, which is a great place to be. I'm sure you had a great time in Amsterdam.
Oh, yeah.
And after that, he went to Caltech, where he was a Thomas Prize Fellow and research faculty. And after that, he joined very recently the Harvard faculty. So I'm pleased to hear today about ill-posed inverse problems in radio astronomy. And Liam, the floor is yours. Thanks very much.
Thank you very much. I actually get to give a whole talk today without mentioning fast radio bursts, which is really exciting. This is like the first time in 10 years. Okay, so I'm going to be talking about reconstruction problems in astronomy. Probably I only have time for 2D reconstruction problems, so image analysis basically. If there's time, I'll talk about 3D reconstruction as well. Specifically, I'll talk about the so-called ill-posed inverse problems, at least in radio astronomy, which is a field that's had just incredible gains in the last 10 years in the computer vision community outside of astronomy. And so the kind of open question that I want to try to address is, should we expect to see similar gains on computer vision tasks within astrophysics that have been seen on these sort of real world images? It's really not guaranteed. The noise properties are different. We tend to have sparser images, but we'll see. Okay, so what do I mean by inverse problem? Well, these concepts are almost so intuitive to us scientists that we don't really have names for them usually, but the basic idea is with an inverse problem, you start with the results, some corrupted, noisy data, and you try to infer the causes. The forward problem is you start with some model and initial conditions, and you try to predict the outcome. So for example, suppose you have some sheet music and a list of instruments. Can you predict the spectrogram that's going to produce? The inverse problem in this case is if you have the spectrogram or you listen to some music on the radio, can you try to unbake the cake? Can you try to figure out what went into that? Or suppose you want to image your patient's brain and you put them in an MRI and you end up with this noisy, corrupted image of a slice of their brain. Can you undo that MRI and try to reconstruct what the true brain looks like? More relevantly to this talk, you have some true sky, you image it with your interferometer or any telescope. You have what we call in radio astronomy a dirty image. Can you invert that and reconstruct the radio sky? So just to show a really simple example of how unstable these inverse problems can be, suppose I have this simple linear system, so a 2x2 matrix that looks like that. I have some ground truth x, which is just 1, 1. The y, the data that I observe is this vector, 3.98 to 2.01. And so if I only had that, but I knew my measurement operator, I can just recover x by multiplying my data y by the inverse of that matrix A. See, we recover 1, 1. The answer was 1, 1. If I add a tiny little bit of noise at the 1% level, so I change this y vector, before it was 3.98, now it's 4 and 2, again, a tiny little bit of noise. And then I do the same thing, just multiply my data by the inverse of that operator A. Now I get the totally wrong answer. Right, so this is what we call an ill-posed inverse problem. In this case, it's because it's unstable. We call these problems well-posed if the following 3 things are true. A solution exists, the solution is unique, and small changes, and the data are not going to lead to huge differences in the outcome. They're ill-posed if one of these is not true. Okay, so for decades and decades, computer vision folks have been working on these sort of classical ill-posed problems. things like deblurring, where maybe you have a little shake in the camera, or you have some unknown blurring kernel that you're trying to invert and recover the crisp image. And it really wasn't until the last 10 years in this sort of deep learning revolution that a lot of these problems started to be solved. Inpainting is another classic one. Suppose you have parts of the image either missing or corrupted. How do you fill those in an informed way? You really just can't do this with classical algorithms. Superresolution, which is something I'll be talking about later. This problem where you have a low-res version, maybe downsampled, and you want to produce a recovered, high-resolution, upsampled version of that image. Also highly ill-posed, also tremendous gains in the past 10 or so years, thanks to deep neural networks. 3D reconstruction, you can imagine there are lots of reasons why in video games or computer graphics or any other case, there are lots of other real-world cases where it's really useful to be able to go from 2D images, projections of the 3D field to a reconstruction of that 3D field. And so again, just to reiterate, the question is, will these things translate into astronomy? You can think of lots and lots of places where it would be really useful to go from, say, a 2D image to a 3D reconstruction of that volume, or to make an image sharper, to increase resolution, go below the PSF, image a black hole, do this really high dynamic range imaging of exoplanets. All of these things would be useful, and it's still kind of an open question if we're going to see similar gains in our field. Okay, so let's jump right into interferometry. You might remember that with a radio interferometric array, a pair of antennas is called a baseline, and one of those baselines, which is itself a 2-element interferometer, is going to be sensitive to a single Fourier mode on the sky. The response pattern of that 2-element interferometer is just a sine wave. And so with 2 antennas, 1 baseline, you cannot make a nice image. But if you use all roughly n squared baselines of the n antenna array, you build up sensitivity and you fill in those spatial frequencies that you were missing. And so if we combine the response in the sky of all of those antennas, we end up with a PSF that might look something like this. Now you'll notice in radio astronomy, and actually in a lot of PSFs in astronomy, this is not a simple Gaussian blurring kernel, like in the previous examples. It's highly non-local. And then we have this little peaked Gaussian component here, but then we have these 6 struts that go in different directions. So you're sensitive to a very bright point source over there, and you have to solve this much harder global problem for deconvolution. And this is what we've been trying to do for many, many decades in radio interferometry. You have some PSF, which is determined by your observing frequency and the positions of the antennas. And that gets convolved with the true sky. And our goal in image reconstruction and interferometry is to deconvolve this thing we observe, which we call the dirty image, and reproduce a reliable reconstruction of the true sky. The oldest algorithm, the algorithm that's produced the most science and been used by the most radio astronomers, is called CLEAN. So CLEAN, first of all, assumes that the sky is made of point sources. I'm going to tell you kind of the original version of CLEAN. There are more complicated variants, but this is called hog-bomb CLEAN. So you assume the sky is made of point sources. You assume that you can iteratively subtract off the effect of the PSF by starting with the brightest point source and working your way down. So the idea is we have this dirty image in the middle. We then figure out where the brightest point source is. In this case, it's right there. And then we have this model, which is being shown on the right, where I'm going to keep track of all the point sources that I've subtracted away. So now I have a residual map. I've removed that bright point source. I do this until I reach some stopping criteria. And then I say, okay, here's my model. I'm going to reconvolve that with roughly the angular size. A Gaussian has the angular size of the central component of the PSF. And I'm going to add back in my residual, and this is my reconstruction. So you can probably see why this is not optimal. It's really easy to poke holes in CLEAN and make fun of it. It's also fun. And so most imaging conferences you go to in radio astronomy, people are complaining about CLEAN, but there's something to be said for something that sticks around this long and produces this much science. So clearly something's going on there that's useful. Maybe the iterative nature of it, maybe something else. But even with these really basic assumptions about deconvolution, you can already do pretty well. So if we go back to the VLA, I don't know if you can see it very well in the middle panel, but the PSF looks something like this. A snapshot image, meaning no Earth rotation synthesis, just maybe 10 minutes or something on a source, will look like this. This is, if we deconvolved it, we would see a lobed radio galaxy. But you can tell just from the so-called dirty image that you really have to go at it with deconvolution. You're not producing a nice image directly. You produce something that looks like a bunch of PSFs, and you really have to reconstruct. If we start increasing the number of antennas, the VLA, by the way, has 27 antennas. If we go to 50 or 100 or 1,000, the thing we're producing directly already starts to look like a nice image. We don't have to do this painstaking deconvolution that we did for more sparse interferometers. So once we get to, in this case, 2,000 antennas, we have a nearly filled aperture. And the thing you're producing, the so-called dirty image, is no longer very dirty. It's actually quite a nice image. It's not perfect, of course. You're going to see ringing effects, but it's much, much better than the PSF of just a snapshot with the VLA, for example. And this is part of the concept behind the so-called DSA 2000 antenna deep synoptic array. The idea is if you have 2,000 antennas in a modest footprint, in this case, 15 kilometers by 18 kilometers, you're going to fill in all those spatial frequencies, and you're going to have a nearly uniform sampling of the aperture plane. And the thing you're producing is going to look a lot more like the images that come out of an optical or IR camera, which is why we call this sort of the first radio camera. Here are the basic specs. It's 2,000 5-meter dishes, observing between 0.7 and 2 gigahertz. The angular resolution in the middle of the band is 3.3 arc seconds, and it's highly optimized for survey science. So you can see that in this metric here. This is survey speed, how long it takes to map out a square degree on the sky to a fixed depth as a function of continuum sensitivity, and it's at least 2 orders of magnitude higher in survey speed than anything that currently exists, and it's higher than SKA and HBLA. You can imagine, because it's optimized for survey science, there are lots of different science cases. For example, multi-messenger astronomy. We'll spend about a quarter of our time doing pulsar timing. We'll spend maybe 5 or 10% of our time following up EMGW LVK events. H1, there's a massive 21 centimeter backend with different spectral resolutions. You can see just a comparison of what you get from 10 hours with the VLA on the left for this relatively nearby H1 galaxy compared to 15 minutes, a single pointing with the DSA 2000. Dynamic radio sky, FRBs, I guess I did mention them. Supernovae, TDEs, all kinds of slow transients. Okay, so going back to the comparison of the PSF and the imaging problem with the DSA 2000 versus previous interferometers. Now you can see with this sort of 15-minute pointing, the thing we're producing already kind of looks like a lobed radio galaxy. And so we're in a different regime of image reconstruction. There are some other constraints that we have to acknowledge. One is that the data rate, when you have 2,000 antennas, each sampling the electromagnetic waves 5 billion times a second, the data rate is going to be so large that you cannot possibly preserve the raw data products that previous interferometers preserved. So for example, the raw data rate is something like 80 terabytes a second. That decreases when you produce what we call visibilities, the correlations between individual antennas, but still we cannot possibly save these visibilities to disk. And so everything has to be done in the image plane. We're producing these images directly. And so whatever deconvolution technique you produce, it has to be done without visibilities. So that's the first constraint. The second is that we need the image reconstruction, the imaging, to be automated and fast. A lot of the times, you have some expert in CASA, some radio interferometry expert who spends a lot of time figuring out exactly how to clean the image. We can't possibly do this because we have many, many tens of thousands of pointings and large image cubes. Of course, you want it to be accurate, and ideally you'd be able to provide some super resolution. So access to angular scales below that 3 arc second PSF that I mentioned before. And that's because there's a whole bunch of science cases that happen to be around sort of half an arc second or an arc second. For example, strong gravitational lensing. Okay, so clean can in principle be done only in the image plane. It's not particularly automated. A lot of the times when you see a beautiful image, for example, Meerkat's image of the galactic center, it's because really some expert went in there who knew exactly what they were doing and worked on it for several days. It's kind of by construction not able to provide super resolution. If you remember that final step of restoring with the Gaussian kernel, that basically acknowledges the fact that clean is not very good at recovering high spatial frequencies, and so it convolves it with what you expect the PSF to be. Forward modeling, the sort of RML techniques that were used partially for the EHT image reconstruction, can be very accurate, can provide super resolution, but they require visibility data, which we're not going to have access to, and they're not particularly fast. And so this is why we started thinking about machine learning-based approaches, feed-forward approaches, where you have some network that knows the mapping between the true sky and the convolved image, the thing you observe, and it can undo that in a single pass through the neural network. So again, if we lean on some of the tools that were created in the past 5 or 10 years for these classical ill-posed inverse problems like deconvolution and super resolution, we have a pretty good baseline to start with. And so I created this method, which I call polish. Polish in contrast to clean, because in the case of DS 80,000, the images are already fairly clean. You just take the galaxies and kind of polish them up. And the basic idea is you have this neural network, in this case, a residual neural network, which is going to be trained on a large data set of image pairs. And those image pairs are the true sky, which is forward modeled, and the convolved version of that. You know the PSF from the position of the antennas, and so you can create these image pairs in simulation. So again, the order of operations is you have this true sky, you observe it with your interferometer, which is like taking this 2D sky field and convolving it with your PSF. This produces what we call a dirty image. And then the goal of any reconstruction technique, or in the case of polish, is to feed it to the neural network and output a reconstructed version of this, which, if it's done a good job of deconvolving, it should allow you to super resolve some scales in a sort of signal to noise dependent way. So here's a simulation I built for this. The microjansky radio sky, which is what DS 80,000 will see, is actually just kind of a lot of star-forming radio galaxies. Maybe 10% are AGN. Sometimes you get lucky and there's a large galaxy in your field, but that's a lot of little Gaussian blobs, really. And then we want to account for the fact that we don't actually know the PSF perfectly. There are going to be little calibration errors. The ionosphere is going to impact us. And so we want to warp the PSF in a physically motivated way that accounts for things like calibration errors, the ionosphere moving above us, all these things. And so during training, each of those image pairs gets a random perturbation of the PSF such that it doesn't overfit to the idealized PSF. And turns out it works remarkably well. In this case, you can train on that relatively simple training set where it's just a bunch of Gaussian blobs, a bunch of little star-forming radio galaxies, and then apply it to much more complicated images with larger diffuse angular scales and things like this. And it still does quite well. If we compare it against clean, so here I have just what I call a single channel snapshot image, which means you're not using any Earth rotation synthesis. It's just a single 15-minute pointing and a single frequency channel. So that's why you can see the area rings. So if I try to deconvolve that with clean, I get this baseline result that looks like that. With polish, it's a little crisper and you're achieving you're getting to angular resolution a little bit below the PSF scale. Pairs, of course, not perfect at all. But we do find evidence of super resolution that depends on signal to noise. So here I'm just showing the size of the galaxy on the y-axis in the recovered image as a function of the true galaxy size on the x-axis. And you can see anything below about 3 arc seconds is technically super resolution. And if you're on that y equals x curve, under 3 arc seconds, that's accurate super resolution. Yeah.
Sorry, I will interrupt because I want to remind people that they can ask questions during this. But I will also ask a question. So where is the information coming from for the super resolution case? I mean, you have a limitation on the DSS, et cetera, et cetera. What is it that the neural network is learning? From where is it learning in order to be able to reproduce things that are high resolution?
Yeah, so the neural network effectively learns a prior from the PSF, the forward model PSF in the training data, and your sky model in the training data. So if you think of a really simple example where there's a point source, a literal point source, like a pulsar or something, way, way smaller than the PSF scale. If you think you know the PSF pretty well, then the model should learn that when there's a point source there, it looks exactly like this PSF. And therefore, when I do my reconstruction, I can do something that's a little bit smaller than the PSF, which is technically super resolution. And of course, it's very commonplace to super resolve things astrometrically in lots of fields of astronomy to get the position of a source below the PSF scale. And this comes from the fact that you know the PSF and you think there might be a point source there.
I'm wondering about the influence of the prior on your reconstruction. Right, in the absence of knowledge, essentially every machine learning tool will produce the prior information in. And so if you train with little Gaussian blobs, you can distort them, you can have, ellipsoidals, things like that. But sometimes real astrophysical objects are more complex. In particular, some of the things you mentioned in the beginning have very complex shapes. So have you tried with different priors for the images, and how's the dependence of the reconstruction on which prior you choose?
Yeah, this is really the critical question. How far do you have to push what we call model mismatch before it just stops working entirely? The reason I wanted to start with this kind of low radio galaxy here is because it did seem to show that the algorithm was learning something like deconvolution rather than if you see a PSF, put a Gaussian blob there. You can absolutely break it if you go way beyond the distribution. And so I think the most relevant question, especially for DSA 2000, if we want to use this thing in practice, is how do calibration errors and all the practical things that come with this real-time imaging pipeline break your prior that was in the training data? I think actually the sky model is relatively safe. It's all about what happens to the PSF when you're actually observing.
Yeah, very beautiful. So, how much your method can potentially be used for faint, undiscovered, like events behind the PSF? So if we don't know that there is something and it's just quite a thing that we may have a lot of them on the sky.
That's a really good question. I don't think polish is especially good at digging into the noise. I mean, it's always going to stop at 5 sigma or whatever you're comfortable with calling an actual source. Yeah, the one advantage, not of polish, but of something I'll talk about in the next few slides, is that you can actually produce a posterior on your image reconstruction. The clean algorithm I mentioned before gives you a single reconstruction. And if you see a little smudge, you have to say, okay, is this a noise fluctuation or is this a source? Whereas if you have an accurate posterior on your reconstruction, then you can sample from it and ask how many times is there this little ghost source there. Any other questions?
Okay, I just want to know the true sky image is obtained by I don't know, very deep cleaning. So
Sorry, what was the question?
no, it's obtained by a very deep cleaning algorithm.
Oh, in this case, sorry, no. The true sky in this case is a forward model synthetic radio sky at a gigahertz. So this is simulated data. Yeah. This column here, that's the clean applied to the observation.
Okay.
Okay, yeah, so when we get to this bottom left corner, we're actually kind of at the pixel scale. We've done various sanity checks. For example, you should expect your ability to super resolve a source to go like roughly 1 over the sigma to noise. So you shouldn't do as well on a 100 sigma source or on a 5 sigma source as you do on a 100 sigma source. And we do see this rough trend. This is definitely true for astrometric super resolution, which should go roughly as the PSF scale over sigma to noise. We wanted to apply this to real data. And so I trained a model based on the VLA PSF and obtained some dirty images of VLA observation, which you can see here. If we focus on the brightest sources, this is the clean version. This is the polished version. And if we just zoom in on those bright sources, you can see it really does seem like we're recovering angular scales that clean could not. You can see that this is a lobed radio galaxy as opposed to a blurry peanut. Just to show that this isn't Vmax, Vmin. This is a 3D version of the same. Yeah.
Just quickly,
That's right, Kirsten.
on that clean version, are you using natural weighting?
I actually don't know what the UV weighting was. My colleague Greg Holland gave me this data directly,
Okay.
along with PSF, yeah. But it's a good point. Different weighting schemes can give you different resolution. Okay, so why might we want super resolution? Why do we want to go from 3 arc seconds to 1 or something like this? Well, as I mentioned at the beginning of the talk, there are a bunch of cases where it'd be really nice to have ever so slightly sub-arc second imaging from the DS8000. So for example, I think we'll find a huge number of strong lenses. The problem is we're right at the cusp of where the typical Einstein radii are galaxy strong lenses. So to date, there's something like 100 known radio lenses, maybe something like 1,000 lenses in total, most optical IR. But with Rubin, Euclid, and I'm claiming the DS8000, we'll increase this by many orders of magnitude to 10 to the 5 or 10 to the 6 strong lenses. And the reason the DS8000 is useful for this is because the strong lensing optical depth, which is this black curve here, is a quickly rising function of source redshift. And you can see radio sources to very far away. The redshift distribution of the DS8000 with the SKA is much, much deeper than Rubin, for example. And so the mean optical depth is very high. And with 1 or 2 billion extragalactic sources and an optical depth of 10 to the minus 4, you end up with a huge number of sight lines that are strongly lensed. The problem will be finding them. And the problem will be recovering the ones that are below this 3 arc second or 2 arc second angular scale. It's 2 arc seconds at the top of the band. So why do we want all these lenses? V can correct me if I'm wrong, but I think for almost all applications of strong lensing, it's really useful to have an enormous sample from which to draw sort of golden subsamples. Whether you're doing dark matter stuff and trying to figure out the matter distribution within deflector halos, looking for high redshift sources via magnification. We've all watched in amazement as James Webb finds individual supergiants at redshift 2 or 3. This is because of magnification and the magnification bias we can get. You can discover really special sources like so-called jackpot lenses where you have 2 Einstein rings. This allows you to break things like the mass sheet degeneracy. And then in the radio, it's kind of specific to the radio, we'll have polarization information for tens of millions of sources with the DS8000. You can measure things like Faraday rotation. And if you have a strongly lensed radio source for which you can measure Faraday rotation, you get the RM from the 2 different paths that it takes. And so you can start to measure magnetic fields, cosmic magnetic fields in the in and near the deflector galaxy. And then finally, you can build up a sample for what's called time delay cosmography, where you use the gravitational lensing time delays to try to measure H0. And again, in this case, I think these are really limited by systematics partly, but also limited by the fact that we've only done this for a handful of sources so far. I think the sample in the Holy Cow paper that claims to get H0 to 2.4% or whatever was just 6 systems. So you can imagine if we had several hundred or even 1,000, we could do a lot better.
Sorry, I have a question online. Are you able to recover similar fluxes to clean, et cetera, as absolute versus relative?
Yeah, so when we get down to the noise floor, we recover the same sources. We did a sort of comparison where you ask which algorithm is more likely to hallucinate and which algorithm is more likely to miss really dim sources. And we actually found that clean, or at least our implementation, was hallucinating more often. That is, putting a point source at the position of a noise fluctuation.
Yeah, a quick question. So if the resolution is so important for this science case, what are the trade-offs that define the resolution of these things without? I mean, why is it a 3 arc-second machine instead of a 1 arc-second machine?
Yeah, it's a fair point. I mean, if we were to stay in the same observing band, of course, we would outgrow our valley by a factor of 3. We only have 18 kilometers in this direction and 15 in that direction. If we wanted to go to higher frequencies, then now you have a less filled aperture, and you're kind of moving away from this radio camera concept. Don't know how strongly dependent the choice of the band was on pulsar timing, for example. I don't think you want to be at 4 gigahertz for pulsar timing, and since the collapse of Arecibo, we really need something in the US for pulsar timing. But yeah, it is a good question. I mean, why not just go to higher frequencies, or yeah.
So that you don't need AI.
Yeah, that's right. Well, I mean, we'll come up with a reason to get 200 millisecond resolution. Yeah. Okay, so the idea is if you can get a factor of a couple or a few in super resolution with one of these learning-based algorithms, then you can claw back a factor of 2 or 3 or more in strong lensing systems. And here's an example, a very simple example, where I have the dirty image, the thing we observed on the far left, the true image on the right, and then a polished reconstruction in the case of 2 strong lenses. So you can see it's not perfect. It's clearly missing this little bump here. Doesn't really see this as an arc, but it does a much better job with Einstein ring. Okay, I mentioned this before, but one of the shortcomings of polish and certainly of clean, actually more broadly, one of the shortcomings of a lot of machine learning techniques is that they don't provide uncertainty quantification. So this is a growing field. You can imagine if most of the machine learning research that's been done thus far has been in industry or in computer science departments, there's less impetus to really do uncertainty quantification well. And so what we really like is not just a reconstruction, but also a posterior on that reconstruction. Some uncertainty that we actually trust, which tells us if I see this ring in my data, in how many samples from that posterior is that Einstein ring actually there? So the first way we tried to do this was converting polish into a Bayesian neural network. The basic idea is it would now output both a mean reconstruction and a pixel-wise uncertainty. And you can do various things to the loss function and try to make it look like this Bayesian neural network. It didn't really work. I don't know, but by show of hands, have people here worked on uncertainty quantification in machine learning before? So yeah, maybe I'll just ask the audience, what was your experience like trying to reproduce realistic posteriors in machine learning problems?
It's perfect in training samples.
Perfectly in the training samples, yeah.
Perhaps less if there is an decrease in simulation there.
Right, yeah, any model mismatch throws it off,
Yes.
yeah.
Also, they are badly calibrated to be right. They are over, well, it depends how big is your model, but if you have to do it on a neural network, you have to do shortcuts to the real Bayesian
Yeah,
way, and then typically they're over confident.
yeah. Yeah, this has been our experience too. You produce this posterior, and then maybe you simplify everything and forward model the posterior, and they don't agree at all. I think there's another comment right there.
The question is, why do you start with Bayesian? I mean, there are normalized flow approaches, right? They share certain similarities and also will help you to reconstruct the posterior. And in our experience in Heidelberg, this can work much better and
Yeah.
be much faster and much more amortized in a way. than standard Bayesian.
Yeah, yeah, so we've actually kind of discarded this approach. I think the reason we chose it initially because it seemed like a small perturbation to what we'd already done. Just change the neural network architecture to output 2 images instead of 1. You add weights to each node, but yeah. We're trying a new approach, and this is with one of my colleagues at Caltech. This is Ray Wu. He's a PhD student in Katie Bauman's group. And he's developed this method not for astronomy and not necessarily for deconvolution, but which uses diffusion models as an image prior, and then tries to solve inverse problems in this iterative way, kind of like Gibbs sampling, where you first sample from the posterior, and then you do a likelihood step, and you kind of go back and forth. And it's proven very successful, at least for some of these kind of like deblurring problems and super resolution in this case. So we're trying to take this work, and he's leading it, but we're trying to apply it to radio interferometric image reconstruction. So the idea here is that you have this diffusion model, which has proven really just a fantastic tool at representing very complex image priors and mapping image distributions. And then you have this more analytic likelihood step, which is the term that enforces data consistency. And then you go back and forth until, kind of like clean, you reach some stopping criterion. And the nice thing about this is, one, you feed it directly to PSF. It doesn't have to learn from the data and store that single PSF as a prior in the weights of the model. In this case, every time you try to do the inverse problem, you feed it the PSF and the noise properties. The other nice thing is that it actually does provide a posterior. So on the right, you're seeing a GIF that's just stepping through different samples from the posterior of the reconstruction. And you can see, kind of like what we were talking about before, if you look at this faint galaxy here, this is the ground truth, so it doesn't have noise. You can't really see the noise scale. But it's kind of popping in and out. Some of the reconstructions, it thinks there's something there. Some of the reconstructions think there's nothing there. And in the higher noise case, you end up with hallucinations. If you look in this corner, they're kind of flickering in and out. So this is still early days, but there are at least ways of going after uncertain quantification for the super resolution and the deconvolution that we're talking about in radio astronomy. Okay, the last thing I'll mention is a project on 3D reconstruction. So I mentioned this a little bit at the beginning, but the idea, at least for a lot of real world applications, is that you have multi-views of some scene, and you have some projected quantity, like an image from different angles. And then the goal is to create a 3D model, do a 3D reconstruction of the thing that produces those 2D images. So this is an inverse problem. It's typically highly ill-posed. Much worse for us in astronomy because unless you're looking at the sun, it's always single view, right? So we only have one viewing angle of the cosmos, and therefore we're always going to be taking this 2D data from a single angle and trying to invert 3D information. In this case, Brandon is also actually a Caltech PhD student who I worked with for a few years, and he's taking weak lensing data and trying to do 3D dark matter reconstruction along that line of sight. And he's using the so-called neural radiance fields, or NeRFs, for this task. The basic idea is that you initialize with some random volume. Of course, you don't know anything about the distribution of dark matter when you start. And then you ask, it's okay. And then you ask, how can I update the weights of my neural network that are going to represent this 3D field, that are going to produce the shear and the convergence that I see in weak lensing? And so this is based on these things called neural radiance fields. Again, this is from computer graphics. We're working with one of the co-inventors of NeRFs, Practical Srinivasan, where the input of your neural network is a coordinate, XYZ, so where you are in the field, and the output is some property of that field. In our case, the density of dark matter, or actually the refractive index technically. So we find that we actually do pretty well. Certainly compared to lunar filtering and traditional methods, especially if we have information about the light sources. So in the cosmological context, that means, you know, the 3D positions of the galaxies that are being weakly lensed, you have their redshifts. And so now we're starting to do more realistic forecasts in the case of kinematic weak lensing, for example, where you actually remove most of the shape noise because you have the kinematics of the lens galaxy. So I think I'm at the hour. Oh no, I'm not even. I'm early. But that's all I had, so I'm gonna wrap up here.
Questions from the audience? Yeah.
Thank you very much. Yeah, so I have a small question about, you mentioned that you loaded the visibility data and then because your network input is a dirty image. However, you still need to convert the visibility data to dirty image that is really also need to use able to do that. So is it possible to use the visibility data as the input of the neural network and to train? Is it possible to get the clean image?
Yeah, certainly. You could imagine using ungraded visibility data and reconstructing from that. It's just that this technique was built for DSA 2000, where that data is not preserved. So you do gridding, imaging, everything is done on the fly, and the thing that's produced by the real-time pipeline is a dirty image. So that's all you have. You can of course go back to gridded visibility data, it's the same thing, but you no longer have the ungraded raw visibilities.
Thank you.
But you could easily, for a different application, you could retrain polish such that it learns the mapping between raw visibilities in the sky.
So you said that you train, you train everything, you put noise into it, and you do very well. But then when you go and observe, you're gonna, of course, have some calibration issues. What are your plans for when that happens? Are you gonna use some reinforcement learning, calibrating it with?
Yeah, I think if we stick with this sort of polish paradigm, this very simple thing where you have a trained neural network, you input a dirty image and it outputs a reconstruction. And I think what you want to do is you want to have two inputs now. One is the dirty image and one is your best guess at what the PSF was at that pointing. And then hopefully you can inject physics into that calibration errors that you kind of know about what the tech of the ionosphere was at that hour or whatever. Yeah. So I guess at the time of inference, incorporating more information about the observation.
We have a question online, if you wanna unmute yourself and go ahead and ask the question.
Hi, I have a question about the procedure. I guess, so at essentially every scan or whatever it is that you're taking data, at every scan time at which you're writing the data, are you saving the dirty image? Is that what you're doing?
Yeah, in the case of the DSA 2000, you're constantly creating real-time images, and you are effectively discarding the ungraded visibility data.
Okay. So then another question I have, if you don't mind, is that so all of this is just continuum, right? Effectively one channel, a single channel.
Everything I showed was effectively single channel, although the input of the neural network it is a data cube. It's just in this case, the frequency dimension was 1.
Okay. Yeah, I mean, I guess I'm thinking like, if you have very high spectral resolution, how well all of this work, etc. So, but I guess if you're saving the dirty image, yeah, it should be okay. Okay, thank you.
I think that's a really interesting question. And by the way, I should say, I'm looking for people to collaborate with on this. I really want to continue this reconstruction work, and I personally don't have time to write the code anymore. So would love to work on this with somebody. This is an open question, how we handle the multi-frequency data, especially the H1 image cubes.
Josh, thanks for the great talk. Could you say something more about the sort of dynamic ranges that you tested the algorithm? What I could see in the reconstructions you've shown, like sigmas in the few tens. I wondered if you tried with ultra bright sources in the field, how well the algorithm still works.
Yeah, this is the critical question. I think the dynamic ranges of the image in the test set were of order 10 to the 5. So getting close to the actual expected dynamic range that you get from the full 10 square degree field of view. So that means there are cases where there are really bright sources blinding out all the micro-Jansky sources. And it does reasonably well. I think in those cases, we should really do something more like clean, where there is this iterative approach, where you first remove the thing that's 100 millijanskys, and then you get on with the deconvolution. But out the box, it works reasonably well.
So you already mentioned having more information from other all sky like public surveys. So Euclid, for example, so obviously going to have a ton of data in the optical. So how can you utilize information from other bands or wavelengths to maybe better understand the nature of radio sources that you detect?
Yeah, it's a really good question. I mean, I've thought a lot about this. It's a big question, but maybe I'll narrow it down and just talk about strong lensing.
Yes, please.
Yeah.
I have some interest in that.
Yeah. In the case of strong lensing, of course, you have Euclid and Rubin and Roman, which may end up doing this 4-pi survey or whatever. So first and foremost, you'll get redshifts, ideally, most of which will be photo Z, some of which will be spectroscopic. And so that will be essential, because just to, a radio arclet on the sky about which almost nothing is kind of useless. And so, yeah, cross-matching, getting redshifts, things like this will be extremely important.
Yeah, so my question was very similar to Jonathan, but maybe I'll expand it to ask, are you running the algorithm exclusively on single pointings, or are you collecting like mosaic data and then running it?
Yeah, it's being run on single pointings at the moment. But yeah, the mosaic question is an important one too. Are you thinking in terms of what happens when you combine the mosaic, or do you mean because the PSF is slightly different?
Both, yeah, all of that. Yeah, and especially if you have a bright source out in the field.
Yeah.
Sometimes with your mosaic image, you can better reconstruct your image, right?
Yeah, definitely. Yeah, for the PSF question at the moment, before we start doing things like including the PSF as an input at the time of reconstruction, at the moment we just effectively fine tune the neural network with a few more iterations of training for a different pointing. Like you do 99% of the work with the full training, and then the PSF is slightly different because you're pointed over there, and so you do a little bit more training.
How do you monitor the ionosphere to know what is going on? And on what timescales is it needed? I mean, there are these extreme events, which of course you don't have to really worry about, like very, very luminous gamma ray bursts that actually change the ionosphere. And a second question, if I can ask too, is the resolution that you're talking about, it seems to be guided by point sources. What if you're interested in resolving jets? And is that a separate algorithm that you've developed? Because that's certainly of great interest in quasars.
Yeah, to answer the second question first, it would be the same algorithm. And the hope is that you build this algorithm that is not just good at maybe getting an arc second instead of 3 arc seconds, but is also good at recovering diffuse emission on much larger scales. To answer the first question, yeah, so there are different ways that people monitor tech as a function of time, the total electron column of the ionosphere as a function of time. In our case, we'll probably be doing it from the data itself. I mean, you'll see tiny little shifts highly correlated on the sky of the positions of known sources. So even just if you use NVSS, like a catalog of bright sources, and you look at their shift on the sky, you can effectively solve for the ionosphere. The timescales that are the relevant timescales, tens of minutes to hours. So obviously lots of diurnal variation from the sun rising and setting.
There. Maybe I did not pay enough attention to the earlier part of your talk, but can you tell us a little bit more about the architecture of Polish in terms of what sort of actual neural network it's using? I thought I saw there was some residual units there. And how flexible is it to accommodate things like vision transformers and other things that are being currently used for image data?
Yeah, you're right. So it's a residual neural network. It's actually fairly simple. I would say when I first started working on this, in my mind, polish was this method where you basically learn the mapping between the dirty image and the true sky, and you can swap in any architecture you like. So for example, if you look at the 2023 super resolution imaging competitions, the vision transformers do very well. And so you can easily just replace what's called WDSR. You can easily replace that with a different architecture. But yeah, these simple residual convolutional networks have proved pretty good at super resolution.
Thank you. We still have a few more minutes for questions, comments, complaints. So I do have one regarding this, what do you call it, the double Einstein ring thing. You showed an image there. Is that an example of one that has been found? And what's the big deal about them? What is it that can be explored if you have two Einstein rings?
So, oh, please, go ahead, Big.
Okay. This,
Actually, where's Duncan?
I'm-
I'll put you on the spot. So basically what you're looking at here is a deflector that's closer to us, and then two sources at different redshifts. So basically what you're doing is you're taking the ratio of the distance between the two sources and you and the deflector, and through that, through cosmology and Einstein radii, you can get omega matter and other things. And if you can, so actually I didn't want to steal your thunder, but basically with the survey that I'm leading, we're finding that probably about 5% of the systems are like this, compound lenses. And you can only tell them with high resolution Hubble or space-based imaging, but you can find them on the ground, which is great. And then when you can actually get high resolution imaging, you can identify them. And then spectroscopy doesn't matter what the resolution imaging is, so it redshifts. So we're actually hoping to build the sample of compound lenses to do cosmology. But I do need someone who can build neural network lens models, anyone, because that's also right now with all Memphis.
anyone in the room?
Sure. I hope they answered.
I mean, they seem way too common, to be honest.
You know,
There's 1,000 lenses. Why is there even one of these? Like,
space
if-
is full of stuff.
yeah, I know, but shouldn't it be the optical depth squared? I mean, it's like, should be 10 to the minus 4 times 10 to the minus 4. For all galaxies, and yet there's like 5 of these things.
Yes, actually, do you mind?
So you mentioned that this algorithm would also work really well for diffuse emission at larger scales. So I was wondering how well can it work, for example, when you observe galaxy clusters and we see these radio diffuse emission really permeating, like, like nanoparsec scales.
Yeah.
How well can it actually work there? Because I think like this is better for this point sources, right?
So actually, one of the key advantages of doing something like polish or any machine learning based approach is that unlike clean, it doesn't make an assumption that the sky is made of point sources. So the de facto standard algorithm is clean and it assumes that everything is point sources. There's been some alterations to that, but basically there's the strong assumption that things are compact and small. And so hopefully learning-based models will do a lot better at the diffuse emission. I haven't tested it on something like a galaxy cluster, but it would be interesting.
Right.
Yeah, can you explain a little bit more how much you can actually put constraints on the magnetic field based on the polarization and lensing and work on those actually things? And for instance, the bigger two modes and other like correlation, EV correlation and so on, they can put constraints on the magnetic field, but they have never used, I mean, of course, that's in the context of EHT, which are by default lens. So I want to know, like in general, how much lensing can help you out together with polarization to put constraints on big field.
Yeah, so this has been done in the past where, I mean, technically what you're measuring is the line of sight integral of NE times B, right? Or
Right.
yeah, NE times B dot DL. And so you're measuring this this weighted sum of the magnetic field strength with the amount of plasma there. So you don't quite get the magnetic field directly, but yeah, you end up seeing significant differences in these lens polarized sources that have been detected in terms of their RMs.
The fact is that, especially around the basically black hole, like a supermassive black hole, magnetic field is very strong. So you can really discriminate between those and basically fluid velocity. That's what they generate. But in general, I mean, again, the question is that if you are in a if you are in a actually medium that they are almost comparable their effects, how much you can like distinguish between the two?
Yeah, maybe I don't fully understand the question, but we can talk about it after.
Okay.
It's definitely the case that intergalactic, circumgalactic magnetic fields are very, very weak. And the only way you can see this difference is if the two lensing sight lines get pretty close to like the ISM of the deflector doxy.
Okay, we can discuss, yeah.
So we'll have one more officially, official time question, and then everyone is welcome to hang and ask again more questions after that.
Yeah, so is there any value in using your neural net prediction, or maybe a suite of them to get like an image and a variance in your image? And then just using a regular old optimization algorithm to do kind of a maximum likelihood on every single pixel in your image?
Yeah, although I'd be worried about a per pixel analysis, because the thing you really care about is uncertainty and correlations between nearby pixels. Like one of the issues with the first approach that we tried was that we were estimating per pixel variance. And so if you have something as complicated as a strong gravitational lens or something, you don't want those pixels flickering on and off independently. You want them to know about each other and for it to tell you whether or not that structure is real as a whole. I'm not sure I addressed your question, but.
You know, would any of that be encoded if you had a variance image getting spat out of your neural net? I don't know,
Yeah, I'm not sure.
maybe some cross correlation image.
Yeah, you can imagine storing a covariance, a limited covariance that's 10 pixels or something.
Let's thank Leon again for a nice talk. But look out to us and looking for collaborators, so reach out and feel free to hang and ask more questions. Thank you.